Welcome to lecture number 26 for ECE 461 control systems, meaning design specs using root locus. Now where we're at, we've got a couple techniques to design feedback controllers. I can use gain compensation, just crank up the gain and adjust till you get your desired overshoot, like 20%. If that's not good enough, if I need a faster system, I can use the lead compensator. The lead compensator pulls the root locus left, speeding up the system. Or I could use a PID compensator. What that does is the I turns a type 0 system into a type 1 system. The PI adds a 0, lets you speed it up. Or PID lets you add 2 zeros, speeding up even more. Now in general, the idea is you add pulls and zeros. You add a pull at s equals 0 if needed to make the system type 1. If it's already type 1, don't make it type 2 because that tends to make systems really hard to stabilize. I then add zeros to cancel pulls to speed up the system. And to make sure I have as many pulls as zeros, I then add pulls. Perhaps one pull at the origin, all the rest of the pulls out of harm's way, like 3 to 10 times faster than the plant. That's pretty much the design procedure. The resulting K of S, the resulting compensator, may or may not have a name. If you don't care about having a specific name for it, it's just a bunch of pulls and zeros. That's really the design procedure in general. Add a bunch of, add a pull at s equals 0 if you need. Add a bunch of zeros to speed up the system. And then clean it up, finish it off with extra pulls to make as many pulls, number of pulls match the number of zeros. So for example, let's take the following fifth order system. The one we've been beating to death for quite a while. Suppose my requirements are, I want to come up with a compensator so there's no error per step input, 2% settling time of 4 seconds, 20% overshoot for the step input, and have a finite high-frequency gain for the compensator. Now translating, what that means is I want a type 1 system that gives me no error per step input. The real part of the closed-loop dominant pole should be -1. The angle damping ratio should be 0.4559, gives me 20% overshoot. Put those together, that says my dominant pole is at -1 plus J2. And however many zeros I add with the compensator, make sure you add that many pulls as well. So the number of pulls has to be at least as equal to the number of zeros. So to start out, here's my target. I want to put the closed loop pole at -1 plus J2. If I just take the system, it doesn't meet any of the requirements. To make it track a constant set point, I need to add a pull at s equals 0. Now these two pulls come together, split apart, and it's way too slow. So get rid of the pull at -0.32. Now the pull at s equals 0 and -2 come together, split apart, and I'm still too slow. So get rid of the pull at -2. At that point, I have a system that gives me the root locus here in blue. It's too fast. That's actually what I want. Start canceling pulls until I'm too fast. What I've done, I've added 2 zeros, so I have to add 2 pulls. One pull goes to the origin. That second pull goes over here somewhere. As I slide that pull around, that's going to repel the root locus. Eventually repel it, so the root locus passes through -1 plus J2. Find the spot. Find the spot where I push the root locus through -1 plus J2. The way you do that is use the angle condition. At any spot in the root locus, angles add up to 180 degrees. So this is G times K. I cancel 2 pulls, add 1 pull at the origin. The second one, I don't know where it is, but it's wherever it takes to make the angles add up. So let's analyze everything that I do know. Ignore this A term, analyze everyone else, and the total angle is -160 degrees. That means that A has to provide -19 degrees, or 1 over s plus A gives -19 degrees. Angle of s plus A is plus 19 degrees. So now I can use trig. I've got this spot right here, -1 plus J2. This angle is 19 degrees. So the x-axis is 2 over the real part is tangent of 19 degrees, or this distance is 2 over tangent of 19 degrees. The real part is that distance plus 1, plus the real part of where I want to put the closed loop dominant pole. That gives you A is 6.8046. Now I have K of S, everything except for K. Here's G times K. Evaluate g times k at your design point. In this case, I get 0.039 at 180 degrees. The 180 degrees is good. That tells me that this point's on the root locus, and it better be, because that's why I picked the pole at 6.8. That point put this point on the root locus. If it's not on the root locus, you made a mistake, and typically what happens is you forgot to add that 1. But as a check, it's got to add up to 180. This one does, but the gain's wrong. At any point on the root locus, g times k is 1. To fix the gain, that's where k comes in. K is whatever it takes to make the gain 1, or 1 over 0.0392. K should be 25.49. So here's my compensator. And I can check. In Matlab, here's g of s. Here's k of s. Close the feedback loop, g times k over 1 plus g times k, and take the minimum realization, because Matlab's got a bug with it. What you wind up with is a pole where I put it. And you better be there, because that's kind of how to design my compensator. Plus 4 other poles. This is a 5th order system. I've got to have 5 poles somewhere. So I've got the complex conjugate and 3 other poles. I can check my answer. In your homeworks, this is a good way to check your answers. Makes grading a whole lot easier. There's actually lots of ways of doing this. As long as I've got the right step response, you probably did it right. What I'm looking at here is here's my plant, here's my compensator. The steady state gain is 1. It's type 1, that's what I want. I've got 20% overshoot, and the settling time is 4 seconds. And that's my requirement. I met the requirements. This is a valid compensator given those requirements. If I want to implement it in hardware, what I would do is here's my compensator. Split it up. I've got an I term and a lead compensator. How you split it up is kind of arbitrary. If I split it up this way, here's my PI compensator. I'm going to pick R2 to be 1 meg arbitrarily. 1 over RC is 0.32, and the high frequency gain is 5. So R2 over R1 is 5. The lead compensator, I picked R5 to be 1 meg arbitrarily. Then the high frequency gain is 5, so that makes that 198K. The DC gain is 5 times 2 over 6.8. Gives me the total resistance. R4 then is 449K. And the 0 is at 2.08. 1 over RC is 2.08. Makes C 1.06 microfarads. So there's a hardware circuit to implement this compensator. Again, could also do that in software. In software, we just do that in 2 filters, or 2 stages. Second example. Suppose I have this system. Design a compensator to give me this step response. Now to do that, I have to take the step response, translate it into root locus terms. What that step response tells me is that the DC gain is 1. I want this to be type 1 system. The 2% settling time is 2 seconds, so the real part of the dominant pole is at -2. And I've got 10% overshoot, or 12% overshoot. Tells me the damping ratio is 0.55. Tells me that the pole should be at -2 plus J3. Damping ratio tells you the angle. I know the real part of the pole. From trig, I can calculate the complex part to set the angle. And tangent theta is opposite over adjacent. Gives me my pole. So come up with a compensator to place the closed loop dominant pole at -2 plus J3 while making it a type 1 system. So the procedure, again like last time, here's my target, -2 plus J3. I'm going to start canceling poles until I'm fast enough. Add a pole at s equals 0. The pole at -1 causes trouble, it makes it too slow. Pole at -3 causes trouble, again too slow. Pole at -5 causes trouble. So let's get rid of the pole at 1, 3, and 5. Add a pole at s equals 0, and I have to add 2 more poles to make this third order. Find those 2 other poles so that this point's on the root locus. Basically, stick 2 poles out here somewhere and slide them around until the root locus is repelled and passes through -2 plus J3. To do that, the angles have to add up. Here's my K of S, here's G times K. Take the part that you know, S times S plus 10. At S equals -2 plus J3, That's minus 144 degrees. So this term, the angle of S plus A, must provide 35 degrees. Each one provides the same amount, so half that would be 17.87 degrees. And we're back to a trig problem. The real part is 3, the complex part, 3 over tangent 17.87 degrees plus 2. So A should be 11.301. That gives me the form of the compensator, gives me the form of G times K. And if you feel like it, you can draw the root locus, and sure enough, the root locus is going to pass through minus 2 plus J3. I can check that, take G times K, evaluate at minus 2 plus J3, and the angle better be 180 degrees. Because again, I picked 11.3 to make this point 180 degrees to put that point on the root locus. Gain's wrong. To fix that, add K. K should be 29.4, so there's K of S. And you can check your response. My desired response is I want to pull at minus 2 plus J3, its conjugate, and the DC gain 1. That's the green line. My actual system, here's G of S, there's K of S, here's the closed loop system. Checking the eigenvalues of the closed loop system, one pulls at minus 2 plus J3, that's good. Now take the step response of the desired system, the actual system, and plot them. The green one's my actual system, green one's the desired system, second order. Here's my actual system, fourth order. Again, right overshoot, right settling time, right DC gain. That meets my requirement. And the circuit to implement that, again, would be one that we've already done. Split this up into 3 parts. This would be a PI compensator. Here's a lead compensator and another lead compensator. So that's lecture number 26, meeting design specs. Basically, you add poles and zeros. Add a pole at S equals 0 to make it type 1 if it's not already type 1. Start canceling poles with zeros until you're too fast, and then clean it up. If I added 3 zeros, make sure you add 3 poles. One goes at the origin, the other 2 goes wherever it takes to set the angles right to put your design point, in this case minus 2 plus J3 on the root locus. Then pick a gain K to make the gain 1 at that point. Lecture number 26, meeting design specs with root locus.